Hi coders, today we will solve a problem called as closest binary search tree value, problem number 270 on LeetCode. Till now we have applied binary search on a sorted array where we try to find the target element, a number range where we try to guess the number higher or lower than a given value, and an unsorted array where we try to search for a target element in a rotated sorted array and a sorted array of unknown size. In this video we will try to apply binary search on a tree, a special type of tree called as BST. This problem has been asked by Facebook and Amazon in the past 6 months. So let's go through the problem statement first. We are given a binary search tree. That is, we are given a root node and we can access all the other nodes in the tree using that. We are also given that the binary search tree is non-empty. That is, the root would not be null because there would be at least one value in the tree. Besides the root node, we are also given a target value, and the given value is a floating point. What we want to do in this problem is to return the node value in the tree which is closest to the target. The first approach that is coming to my mind is a recursive linear scan. We travel to all the nodes in the tree recursively and return the node value which has the minimum absolute difference with the target value, which is 5 in this case. The time complexity of this approach is On, and the space complexity is On, that is the recursion stack. The second approach that is coming to my mind is to do a recursive INORDER traversal. Because if we traverse a binary search tree in an INORDER fashion, it will be sorted. And we can terminate the traversal whenever we get the value greater than the target. That is, if we see the INORDER traversal, we will have two answer candidates. The upper bound of the target value, that is 8 here, and the value before the upper bound of the target, that is 5. So either of them would be the answer. Here also the time complexity would be On and the space complexity would also be On because it's a recursive traversal. Now if we think in the direction to optimize it further, let's see if we can use any property of binary search tree to reduce the time complexity to logarithmic. We know according to CLRS, any node value in a binary search tree is greater than or equal to the maximum of the left subtree and less than or equal to the minimum of the right subtree. So let's see if we can reduce the search space using this. We are given a target value of 6.12. The node value is 5. All the values here would be less than or equal to 5. And if we choose any value here, the difference would be greater than 5. So if the target is greater than the node value, we can reject all the values of the left subtree and a search space would be reduced to the node value and the right subtree. If the target value was 4.12, which is less than the node value, by the similar logic we can reject all the values of the right subtree and reduce our search space to the node value and the left subtree. If the target value was 5, we could have terminated our search at the node value itself, because the absolute difference would be greater than or equal to 0 and it cannot be less than 0. So we don't need to traverse in any direction. The time complexity would be O log n base 2, because we are trying to reduce the search space by half at every step, and the space complexity would be O1, because we will follow an iterative approach. Now let's see how we will alter template 1. As we discussed earlier, if the node value is equal to the target value, we can break from the loop and return the node value, that is the target. Else if the target is less than the node value, we can shift our search range to the left, else we can shift it to the right. Here we have typecasted the node value to a double, because here we are trying to compare a node value which was initially an integer to a double value. Now that we have a basic understanding of what's going on, let's try to dry run our code. We initialize the answer to root value, that is 5 here. We have a pointer called node pointing to the root node. I'll represent it using n. Since the node pointer does not point to null, we'll go inside the loop. We'll initiate the node value to 5.0. Since 5.0 is not equal to 6.12, we'll not enter here. Absolute of target minus node value is equal to 6.12 minus 5.0, which is equal to 1.12. The target minus answer is also 1.12. We'll not update answer and answer will still remain 5. Since target 6.12 is greater than the node value, that is 5.0, we'll compare the target value to the node value, that is 6.12 to 5.0. Since the target value is greater, we'll shift our search range to the right and the node pointer will now point to 9. Since the node pointer does not point to null, we'll go inside again. We'll update the node value to 9.0. Since 9.0 is not equal to 6.12, we'll not enter here. Target minus node value, that is the absolute of 6.12 minus 9, which is 2.82, is greater than 1.12, so we'll not update our answer candidate. We'll come here. Since the target value is less than node value, we'll shift our search range to the left. That is, now the node pointer points to 8. Since the node pointer does not point to null, it will go again inside. It will update the node value to 8.0. Since 6.12 is not equal to 8, it will not go inside. Absolute of target minus node value, that is 8 minus 6.12, is equal to 1.82, which is still greater than 1.12, so answer won't be updated. Target is less than the node value, so our search space will move to the left. Now node will point to a null value. Since node is equal to null, we won't enter here and return the answer value, which was 5. So the output is 5. That's all for this video. If you like the video, please hit the like and subscribe button. If you have any questions, please leave in the comment section below. Thanks for watching till the end.